Chapter 4, Section 9 is entitled Applying the Pythagorean Theorem and its Converse. Here we're not only going to be using the distance formula today as it relates to the Pythagorean Theorem, but we're also going to be introduced to the distance formula, which is really the first time we've tinkered with that formula at all. The distance formula is about finding the length of a distance that, I guess for lack of a better term, we would call it diagonal across a coordinate grid, or between 2 points that are at least not horizontal or not vertical on the coordinate grid. So let's go ahead and start off with this first question here. Now this first question is using the Pythagorean theorem. So this question is continuing to use that formula you saw yesterday that says the lengths of the legs of a right triangle squared and then added up is equal to the hypotenuse squared, or in other words, a squared plus b squared equals c squared. And they're asking me here, what is the diagonal length of the projector screen, which is the diagonal line that's dashed as you see going across the projector screen there. So, as you can see, what you do have here is a right triangle. Once we cut that rectangle into a couple pieces here, here is your right angle. Remember, those two sides that make the right angle, these two guys, those are the legs of my right triangle, and that means this other side, the dashed diagonal line, that is the hypotenuse. And what the formula says is that these two guys squared is the same as this guy squared. So we're going to dump that into the formula and say that 3 squared plus 7 squared is equal to the hypotenuse squared, which is what you can see they've written right here. 7 squared simplifies to 49, and 3 squared simplifies to 9. And we add those guys up for 58. So the hypotenuse squared is equal to 58. But remember, c squared is not the hypotenuse, that's the hypotenuse squared. But up here, this side is just the hypotenuse. So to get away from c squared, the hypotenuse squared, or to cancel that out, you take the square root all the way across. The reason that works, again, is because squares and square roots are opposites of each other. So they cancel each other out. So when I take the square root of c squared, that's how I get back to b, or c. Square root of 58, that's 7.62, which is an estimated value there. They've rounded to the nearest hundredth like they did yesterday. So the diagonal length of the screen is about 7.62 feet. Again, that makes sense because the hypotenuse always has to be the biggest number. 7.62 is bigger than my other two numbers, 7 and 3, so that answer in that regards is logical. If I would have gotten an answer like 6, I would have known I would have done something wrong because the hypotenuse has to be the longest side. All right, let's go ahead and go down to number 2. Number 2, we're going to tinker with that distance formula that I mentioned. And again, the distance formula is all about finding the distances between points on a coordinate grid that are not horizontal and not vertical. So let's look at what they've got here. They're asking me to find the distance between J and K. Now, realize here, looking at this illustration of the coordinate grid, some of these would be really easy. Like if I was asking you to find the distance between K and M, all right, you would just count that off because it's a horizontal line. You would say that's 1, 2, 3, 4, 5 jumps there. That's it. Okay? That works. We don't have to use a formula or any fancy rules. We just count. But when I'm trying to find the distance between J and K, that is not a horizontal or vertical line. Going across a box diagonally does not represent the number 1. All right, for reasons that we could prove based on the theorem. The legs of the grid box being 1 each, all right, that's 1 plus 1 being equal to c squared, or 2 being equal to that hypotenuse, which would be diagonally across a grid box. Take the square root of 2. Is the square root of 2 1? No, the square root of 2 is not 1. The square root of 2 is actually 1.414212135562. So about 1.4 units long. All right, so going diagonally across a box is not 1 unit, simply based on the theorem. So we have to have something to be able to help us to find the distances between those 2 points. And right now they're asking us to find the distance from J to K. Now, realize we have other options here. If we don't want to learn the formula, if we don't want to work with that, what we could do is make it part of a right triangle. What we could do is we could draw the north-south and east-west distances between J and K like this and create a right triangle. And then use the theorem, because then we could count these to find the length of the hypotenuse that we could not count. We could also do this one here, this triangle up top. The numbers would be the same. It would just be flipped the opposite way in the drawing and find that distance. But let's say I don't want to do that work. Let's say I don't want to do the Pythagorean theorem all the time. Let's say I want to learn the formula. Let's learn the formula, which is what this is all about. So, we're finding the distance between J and K using this distance formula, and that's what they present to you here in this first line. What the formula says is I'm going to find the difference of the x values and square the result, find the difference of the y values and square the result, add those two results together, and then take the square root, and that will find for me this distance. Well, let's put that together. All right, remember, points on the coordinate grid are always written x, comma, y. So this has an x, comma, y value. This has an x, comma, y value. X represents the x-axis, the one that runs left to right. Y represents the y-axis, ones that run up, down. So point J, to get over to point J, I have to go to -4 on the x-axis and 0 on the y-axis. I'm not moving up or down to get there. So point J here is going to be -4, comma, 0. For point K, looking at where this point is here, from the origin, I didn't have to move right or left to get there, so that's 0 on this axis. But then to get down there, I had to jump down 3 spots, and that's how I ended up at -3. So that point is 0, comma, -3. Okay, so now we know at least where the x's and the y's come from. Let's get now the 1s and the 2's that are on there in the subscript form, these little guys here. So I'm going to go ahead and fill those in here. So the points I have, just rewriting what I have here, I have 0, -3, and I have -4, comma, 0. Again, points are always written x, comma, y, which we've already explained. All the subscript 1s and 2's represent, which I'll sometimes say x sub 1 and x sub 2, all that represents is which set of numbers they are. So I'm going to go ahead, since this is the first set of numbers I wrote, I'm going to put 1s on those guys. Since this is the second set of numbers I wrote, I'm going to put 2's on those guys. If you don't want to write them in that order, if you want to write this guy second and make these the 2's, that's fine. It's not going to impact anything if these are flipped around. If these are your 2's, or these are set over here as your 2's and this set is your 1's, it's not going to impact anything. The end result will be the same. All right, so formula says take the x values and subtract them. So -4 minus 0, which is -4, which is what you can see they did right here, and simplified it down here to get -4. And then over here it says I'm going to take my y values and subtract them. So 0 minus -3, which is of course 3. That's what they're showing you right here to here. Remember, minus and negative changes into plus. Formula says now I'm going to square each of these guys. -4 squared is 16, 3 squared is 9. Then I'm going to add those guys up and take the square root, and the result is 5. The square root of 25 being 5. So this distance here represents 5 units. If you want to see it works, let's do what we said a minute ago. Let's go ahead and draw a right triangle out on there and make sure that that works, because that's going to have to be the hypotenuse. If we draw this triangle in here, this right triangle, right, this distance here is 3 units. This distance here is 4 units. Remember, the Pythagorean formula, not the distance formula, the Pythagorean says if I take each of these guys and square it, 3 squared is 9, 4 squared is 16, add them up, 25, take the square root, that's the hypotenuse, the value of the hypotenuse. Well, when I took the square root of 25, I got 5. Well, what a surprise, because when we figured it out with this formula, it was 5. All they've done to derive this formula is they've just reverse engineered the theorem here. That's all they did, is they reverse engineered this guy to come up with a formula that we can use to find the distance between 2 points without always drawing a right triangle and then using the Pythagorean theorem. All right, so let's go ahead and continue on here. Now the last one here, it says to tell whether the given side lengths form a right triangle. So this is kind of pulling in some information you've heard. Remember, the biggest number in the sides of a triangle, in a right triangle, that largest number always has to represent the hypotenuse. So if I've got 9, 12, and 15, which is exactly what I have here, 15 has to represent the hypotenuse because it's the biggest number. So what the formula says is that these two guys squared is supposed to be the same as the hypotenuse squared. So that's exactly what they're going to do to test it. They're going to take 9 and square it, and they're going to take 12 and square it, and add them up. Well, 9 squared is 81, 12 squared is 144, which is exactly what you can see they're doing right here, and that equals 225. That should be the same as the hypotenuse squared. Well, if the hypotenuse is 15, it should be the same as 15 squared. If that works out to be factual, then that means we do indeed have a right triangle. On the other hand, if that works out and we find out that we don't have that to work out to be a true statement, then that means we have something else that's not a right triangle. Who cares what it is? So let's take 15 and square it. Well, 15 times 15 is 225. Does 81 plus 144 make 225? Or does 225 equal 225? Of course 225 equals 225. So since it worked out that squaring the legs and adding them up was the same as the hypotenuse squared, that means this is indeed a right triangle. And again, it's just me taking that formula that we've already seen and doing something else with it. All right, so let's look at the check it out example here. It says a square garden has a side length of 10 meters. What is the length of the diagonal of the garden to the nearest 10? Okay, so we're going to go ahead and draw ourselves a little square. And what they're saying here is that all the sides of the square, because of course being a square they all have to be the same anyway, the sides of the square measure 10, in this case, meters long. So these are all 10s. And they're going to draw a diagonal across the garden. So diagonal connects non-adjacent corners. So either this one or this one right here. Let's draw this one. We're supposed to find the length of that diagonal to the nearest hundredth. Well, either way you go, the work is going to be the same. Either here you have a right angle or here you have a right angle. That's assured because it's a square. Square has to have 4 right angles, so we know those are right angles. So, if these two sides make up my right angles, these are the legs of what is now, if I use the top triangle, all right, a right triangle. This side is the hypotenuse. Obviously, if you do it down here, 10 and 10 are still the legs. You're still finding the length of the diagonal. Since it's the same numbers, the result would be the same. So, we're finding the length of the hypotenuse, which is the diagonal of the garden. So the formula says if I take the legs and square them, 10 squared and 10 squared, or 100 and 100, that's going to be the same as the hypotenuse squared. So the hypotenuse squared is the same as 200. Well, I don't want the hypotenuse squared because remember that side of the triangle is just the hypotenuse. So what I have to do now to get from hypotenuse squared back to hypotenuse is take the square root. Again, the reason this works is because square and square root cancel each other out. So watch, these guys cancel, just leaves me c. The square root of 200 is my hypotenuse. And when I do that, I get 14.14213562, which as you can see, they've rounded to 14.14. The diagonal is 14.14 meters long.